Okay, let's get started. So if you're picking up your midterm, go ahead and do so while I'm talking. If you haven't, go ahead and pick them up. Please pick them up because my back is killing me from carrying these. And I really want you to have these because they'll be really valuable to you to have as a learning experience. So any questions about the midterm itself? So how many of you are unhappy with your grade? I think everyone is. So first of all, remember that later tests will replace this test if you do better on it, as percentage-wise. Yeah. I'm going to change that because so many people bombed this test. So if you attempted the test at all, it'll replace it. Okay? So for those of you who didn't attempt the test, can't really help you there. But if you attempted the test, later tests will replace it if you do better on the later tests. So regrades. So I imagine quite a few of you are going to want to regrade. So here's what you do. By Wednesday next week, you will need to compile a list of reasons why you think your test should be regraded, staple it to the front of your test, and give it to me. I'll regrade the entire thing top to bottom, as if it was never graded before. And whatever the resulting grade is, that is final and not able to be disputed. So the new grade, if it's regraded, can go up, could be the same, or it can go down. But the new grade will be the final one. I can't hear you. What do you mean extra credit because of time? I can't hear you. You have to speak up. Everyone, shh. Got 10 points on a problem. Yeah. It might, because I might have missed something that I didn't look at before. So I'm going to regrade the entire thing top to bottom as if it was I'd never graded it before. Okay? Yeah.
That's only if we wrote it in pen.
Yes, if you wrote it in pencil, it's not eligible for regrades, as I've said numerous times. If you wrote in pen, then you can. And I made a note already of who wrote in pencil, so yeah, don't write in pen now. So yeah, those are regrades. Any other logistics kind of questions? So on the announcements page, I put a list of what you currently have as your total grade and what I think is a accurate representation in terms of a letter grade for that. So for now, ignore what Blackboard says. Those are just what I have as the official cutoffs, but what is a more accurate representation I have on the announcements page. So compare your total with what's on the announcements page. Okay, so I'm just going to really briefly go over the midterm. Question 1, a lot of people didn't actually read the directions. So for the future tests, what should you do? Read the directions. Because if it says, explain why it's true, don't say, we proved this in class. Does that explain why it's true? Can you say something related that's true, but doesn't actually prove the statement? No, that does not answer what the question is. If you say false, should you give a long explanation of something related to why it's false, but not actually giving a counterexample? No, you need to actually give a counterexample. Most notably, for all the people who I circled that and pointed to part B, you didn't give a counterexample. And in most of them, you didn't give a counterexample anyway. Okay, so part A, this is just what we did in class. Break up the string into 2 parts, run the decider on both parts for all possible splits. Part B is just give an example of a language that is not recognizable, but its complement is recognizable. In that case, it's ATM bar. because ATM is recognizable as we've seen in class. All computations lead to some accepting config. No, it must be at least one path leads to acceptance. They're equivalent because we showed the computation tree approach where you explore the tree breadth for search style. EQ LBA, is this equivalent to EQ TM? No, because it says LBA. A lot of people put, this is the same thing as the ETM to EQTM reduction. Is this EQTM? No, it says EQ-LBA, but it's like the reduction from ETM to EQTM, but for LBAs. The reduction actually works exactly the same, but you have to use an LBA there. All regular languages are decidable, yes, because ADFA is decidable. But you can just run the DFA, yeah.
All regular language is decidable. There's no definition of a regular language recognized by a DFA, so decidable kind of.
So does recognized by a DFA mean the same thing as recognizable? What is the long form of the word recognizable? It's Turing recognizable, and those are for Turing machines. Recognized by a DFA, that just means that a DFA has that language. And we define that language to be regular because some DFA has that language.
So that's saying Turing decidable, right?
Yes, because we've only used decidable in one context. Okay, this one should have been easy, but a lot of people missed it. It's just the fact that we can any finite time operation can be simulated via a whole bunch of increments. And in fact, therefore, the Church-Turing thesis is true. This one, almost no one got right. So the idea here is to think of reductions in that they preserve the answer. So if this language L is not equal to sigma star, so some of its strings have a no answer. So can there be a reduction from something that has some no answers to something that has absolutely zero no answers? Because no string is not in sigma star. So that's why there's no reduction. If you take any string that's not in L, then if you apply this function, this reduction to it, you'll still end in sigma star, but for it to be a reduction, it has to be not in sigma star. But sigma star is every string. So there can't be a reduction there. This one just follows from the definition for recognizers because accepting computations have to be finite in length. And this one most people got is you have to have at least two states because accept and reject states have to be different. Part A for question 2, I don't think anyone got right, or actually even more than half credit on this one. Maybe someone did, I forget. The idea here is that you can show that L is decidable implies that the length is decidable, but the converse is not true. So the reason here is that if you look at ATM bar, for any length string that you pick, then any length that you pick, you can find some string that does not encode a machine in a string. So remember, ATM without the bar encodes a machine in a string with some property. ATM bar is every other string, including the ones that don't encode a machine in an input. So for example, if you pick n zeros in a row, I'm pretty sure that doesn't encode a machine and a string. So, but even if you did, you can just pick some other one and it won't encode a machine and a string. So in fact, for every string, every length, there's some string that's in ATM bar, but that means that the length of ATM bar is every single possible length, so 1 star. But then we know that ATM bar is undecidable. This one, I don't think anyone else got right either. So please review the answer to question 2. So this one, I wanted people to think, well, what is an equivalent condition for checking that some set is a subset of another set? So if we wanted to think A subset of B, that's equivalent to saying A intersect not B is empty. So everything that's in A and not in this supposedly superset B, there's no strings of that form, which means that A is a subset of B. And since we know that A is regular because it has is the language of a DFA, and B is also regular because one star is accepted by a DFA that just loops on one, we can take the complement of that because regular languages are closed under complement, and we can do the intersection of the two, which shows that A intersect not B here is regular. So that means there's some DFA for it. And we showed that EDFA, the emptiness problem for DFAs, is decidable. So in fact, this is a decidable thing to do. Any questions on the first two questions? Okay. Question 3. A lot of people did get this right. So this is not the only solution. I wanted to put a Simpsons reference in there somewhere, but the idea is that we wanted to have that condition that M accepts W if and only if the machine we make has the strings steamed and hams. We can apply Rice's theorem because if you look at the definition of it, if you have two machines with the same language, then either both have both of those strings or neither do. So in fact, it's a property, and it's non-trivial because one of them you can have accept every string, which means it has those two strings, and another one that just accepts nothing, which means it has neither of those two strings. So therefore, one has the property, one doesn't. And so therefore, it's non-trivial. This one, some people did get, which I was happy about. So the key here is that it's not a property, because if you have two machines with the same language, those two machines may have different descriptions. So in fact, one may have its own description in its language and the other one might not, even though they have the same language, because they have different descriptions. So that's what I wanted you to see. This one, for A, I was actually very surprised. Not many people got it, because the key here is that the other language picks the same string for concatenation. Whereas for concatenation, the real concatenation, you pick an arbitrary string in L and another arbitrary string in L. They might not be the same. So in fact, I have a counterexample there, which is all you really needed to do. All you really needed to do for that. Part B, a lot of people did get, which I was happy about. No one did product construction, which I was confused about. But you can do it using product construction because you can define one language, which is the first part, and a language for the second part. And so do the intersection of those two, and then you have a DFA. But this is the minimal DFA for it. But you didn't need to do all those examples, all that minimization. You just needed to produce a DFA, and that was fine. And part C, a lot of people didn't get this one, or just left it blank completely. Because, first off, I wanted you to see the solutions first, and of P set 1, and to notice that it asks to show that it's also regular. A lot of people showed that the majority is decidable. Are those two the same thing? Showing one is decidable versus showing that it's regular? No, because those are not the same class of languages. So, yeah, as I said before, please read the directions. So this one is very similar to P set 2, the Q added one, but this one's a stack version. So I modified it a little bit. A lot of people got part A right, so that was good. I don't think anyone got part B, and I really didn't expect anyone to. I just wanted some steps to do it. It's way too much to write the entire thing there, but I just wanted to see some formal statements about a computation there. If I circled the word computation, it's because you didn't actually write anything related to a computation. So read the directions. That's what I'm saying here. And a lot of people got part C, which I was happy about too. Any questions about the tests? Remember, later tests will replace this one if you do better. Yeah?
This isn't about the really, but for like product construction for GNFA
Mhm.
and stuff,
Mhm.
do you know which lecture to look back on?
The video that says product construction on it.
Is it on?
Hmm. I forget which one. Yeah.
When you said we had 10 minutes left, what question were you expecting us to be at?
Well, there are 5 questions, so I expect 15 minutes each. Hmm.
So we should have been on the last page around there.
Hmm. Or if you're going back and forth, I can't really say, but it should be 4 1/3 question in. But since they're all not equally weighted, it throws it off even more. Other questions? Okay, so let's get down to lecture stuff. So what did we talk about last time? Yeah, we talked about these regular expressions, and what did we show by the end of on Wednesday? Well, we can convert from which way? Regex to NFA or NFA to Regex? Regex to NFA, because we can just look at the smallest pieces of the Regex and then build a larger NFA as we go. And we can work with NFAs because we've already showed that they are equivalent to DFAs via the construction involving those subsets. Hence called the subset construction, but that's not really needed. What was the direction that we were trying to go? We were trying to show not from Regex to NFA, but from NFA to Regex. And the issue was we didn't know anything about the structure of the NFA because we had some structure in the definition of Regex, but we don't have one for NFA. We don't assume anything about the NFA. But we noted that if we have some artist, so it's called an artist conception here. So if we have something like this, where on the right, they may go to other states, but I don't actually care about that. So what could be a regex that describes all the strings that take me from the left state all the way to the right state? Well, either I can go through that top path or I can go through the bottom path. So what is a way I can write that as a regex without the middle state there? Well, I can either take the top path, and so what's a regex for that? A, B star C, because I have to follow the A, take B 0 or more times, which is the star, and then C afterward. Or, so what is that in regex terms? Union, and the bottom path, which we know is D. So that's great. So we can actually, if we can write a regex on the transitions, then we can whittle down the states of this different machine, not an NFA anymore. Then if we can go all the way down to 2 states, and then we have some regex on that transition, let's call it R, then what is the language of that NFA? Well, it must be the language of that regex itself, right? Because there's no other transitions or other states there. So if we can get it down to this form, then we're great. Here's the issue. Could there be a transition in the NFA where something comes into the start state? Yeah, that's possible. Could the NFA have, so we showed that every NFA has another NFA that has exactly one final state. We showed that last time. So let's suppose that this is the only final state of that NFA. Could, in principle, even if it wasn't of that form, could there be a transition out of an NFA's final state? Yeah, that's certainly possible too. And if we had this, then we might not know what the regex's language is in this case. So we'll need to handle that when we talk about this NFA that allows regexes on the transitions. So we'll talk about that now. So a generalized NFA or GNFA, is an NFA with some properties. So one, start state has no incoming transitions. It has exactly one final state with no outgoing transitions. So those are the two things that the two problems that we could have had at the beginning. So a GNFA already avoids those. And every transition is a regex. So it's exactly like an NFA, but we force it to have its start state have no incoming transitions. It has exactly one final state with nothing leaving that one final state. Of course, it could have stuff coming into the final state, but nothing leaving it. And every transition is a regex. So here's a question. Is every NFA a GNFA? No, because we may have something coming into a start state. It may have more than one final state. Every transition already is a regex of sorts. It's a single character or epsilon, but those are already allowed within the regex definition anyway. So 3 is okay, but the first two conditions might not be satisfied. So let's see how we can handle this. So let's say that we have this black box NFA here, and maybe there's something coming into a start state, and maybe it has more than one final state, and there's stuff leaving those final states going somewhere. Could we handle both of those simultaneously? Getting rid of those two problems, I mean. So how do I handle the first one? With having a start state with nothing coming into it. Oh, how about a new start state that epsilon transitions its way to the old start state? Will the new start state now have anything coming in? No, but will I change the language now? No, because since the epsilon transitions in, I'll still get a computation like I did before. So in fact, if we make a new start state with an epsilon transition in, we avoid that problem for number 1. Did you have a question? Guess you didn't have a question. All right. So 1 is okay. 3 is already okay. What about 2? Well, how did we get rid of the multiple states at the same time problem? It would create a new final state and make the other ones no longer final. And how did we connect it up? Epsilon transition out. Yep. Oh, wait, did we just already solve simultaneously the no outgoing transitions problem that we had? Does this there's a single final state. Is there anything leaving it? No. So in fact, we just made a GNFA from this arbitrary NFA. Boom. So every NFA can be converted into a GNFA. So that's awesome. So now, if we can convert a GNFA to a regex, now we're done. Because I can convert an NFA to a GNFA, GNFA to regex. And we'll do an example. Well, let's see. If I wanted, so remember at our example, we removed this state in the middle to make this transition now a regex from the left to the right. Well, what states can I remove here? Or should I remove? Should I remove that new start state? No, that won't help me. Should I ever remove that final state? No. So, because if I did, then I wouldn't accept anything anyway, because that's the only accept state. So, but we can remove any of the other states because all we're doing is we're just updating the transitions along the way. So let's see. suppose that we have this state and we really hate it and we want to rip it out. So the term for this is ripping the state out. And suppose that we have a whole bunch of states coming into this state queue rip. And let's label the transitions, let's call them R1 through RL. And it goes out to other states. Let's actually call those states themselves little r1 through little rl. And then the states that it goes to, let's make these bigger. Let's call them S1 through SK, because there could be a different number of them. And the transitions themselves are big S1 through big SK. So we're just handling the case where we have many things coming in and many things going out. And suppose furthermore that there's some self-loop. And each of these is a regex now because it's a GNFA. Well, let's see. How many transitions am I going to add at the end? If I remove that state, I'm going to be adding some transitions from the left to the right. How many am I going to add? Well, let's see. I can pick any state over here that I like, and coincidentally, any other state on this side. So if I can pick L things over here and independently K things over here, how many transitions am I going to add? L times K. So what would it look like? Suppose I picked Ri, and I want to connect it up to state Sj over here. What should be the transition now? Well, to get into this state queue rip, what regex did I read? Capital Ri, yes. So I read capital Ri. I can go around the loop as many times as I like. So how do I indicate that here? X star. And how did I go from this deleted state queue rip back out to Sj? What regex did I read? Capital Sj, yes. So I'm going to do that exact same thing for all combinations of I pick a state on the left and I pick a state on the right. And so now, once I do that for all of the combinations, I've reduced the number of states by 1. And then now I do it again and again and again until when? I have exactly 2 states. But since we had nothing coming into the start state and nothing leaving the final state, then we must have a situation like this one, where we have a single regex going over, and now we know the regex. So one thing we need to make sure before we go on to an example, am I changing the language here? So don't think I'm trying to fool you here, because I may be fooling you. Am I actually changing the language? Well, let's see. If we reduce the number of states by 1, then if I wanted to go from Ri to Sj, then I need to read a string that regex describes, right? That's how I can go from one state to another. Well, that means that I must have followed Ri in the old picture. Then I followed the self loop on QRIP some number of times, and then I went out to Sj. But that must mean I did the exact same computation as I did before. So in fact, I did not change the language here. Okay, so now let's actually do an example. So let's make an NFA for this. So let's come up with an example on the fly, like I always do. Okay, that's sufficiently complicated. Okay, so here's an NFA for you. What should I do first? Right, is it a GNFA, more generally? No, because it has two final states, right? And there's stuff coming into the start state, so we need to fix this up. So this is where notability is really nice to me, and I can make different colors. So what about the start state problem? How do I fix that? Add a new start state. I'm going to call it QS for start, and epsilon my way in. Is it a GNFA now? No, and why not? Yeah, there's final states, there are two of them, and there's stuff coming out, so we need to fix that. How did we fix that before? Create a new final state. I'm going to call it QF. Make the old ones not final anymore. And how do I connect it up? Epsilon my way over from the old final states and no others. Great, so now we have a GNFA. Cool. So now here's where the class participation comes in. So no points for this, but who wants to nominate a state to rip out? Q1, perfectly valid. It'll actually turn out any state order that you pick is absolutely okay, but you'll end up with a different looking regex. If you apply the process correctly, it'll always be a correct regex, but it may not look the same as if you did it a different way. And actually, in this case, every order will be different. So let's see. So we're trying to rip out Q1 here. Will any transition that does not involve Q1 at all, will those ever change? No, because all the transitions from before involve this ripped state that we are trying to remove. But it didn't touch any other transition at all. So every other transition will actually be the same. So I'm going to attempt to copy this. So this is where notability really shines. All right. So now I'm going to leave the transitions temporarily there, and then we'll fill in the other transitions as we go. Okay. So the way that I like doing this is, so I'm going to put this in dotted so that we remember it was Q1. I'm going to tabulate all the ways we could have entered Q1 from somewhere else and all the ways we could leave Q1 to go to somewhere else. So I call those in Q1. I'm going to make a list, and out Q1, which is also another list. So what are all the ways I can enter Q1 from somewhere else, some other state? Well, Q0 and no other transition goes into Q1. So the only way in is Q0. And if I make a mistake, please stop me. So I think that's the only way you can go in from somewhere else. What about all the ways we can leave Q1 going somewhere else? Well, I can go to Q2 with a different state. So Q2 is a possibility. What's another possibility? QF. Why should I not list Q1 there? We're removing it. So there's no way I can add a transition to Q1 because it's not there anymore. All right. So how many transitions am I going to add looking at these two lists? 2, because it's 1 times 2. So let's do the Q0 to Q2 transition first. So let's see. So there's no transition already there, right? There's no transition from Q0 to Q2. What is actually there? Epsilon. But I can't instantaneously go from Q0 to Q2. In fact, what is between every pair of states that is not there right now is a transition empty set. Because empty set says all the strings in empty set can take you from here to here, but there's no strings in empty set at all. So in fact, between every pair, there's an empty set here. So why is it okay here? Well, if I do empty set union anything, let's say R, what is the result? Empty set union R is R, good. So in fact, we can just ignore them, but they really are there. Okay, so Q0 to Q2. So I'm gonna blank that out for now. Q0. So what are all the ways I can go from Q0 into Q1? What do I read along the way? 1. So I write 1 down. So could I take a self loop at Q1? Yeah, so what is it? It's 2, and how do I indicate going around the loop? 2 star. Great. So 2 star. And all the ways I can go from Q1 to Q2. And what are those? Epsilon. But what is epsilon concatenated with anything? Just the anything, right? Because if I add 0 characters, it doesn't change anything. I could write epsilon here, but it's just gonna clunk up the diagram a little bit. So I'm just gonna leave it 1, 2 star. Okay. So we handled that one. Now we need to handle Q0 to QF. What are all the ways from Q0 to Q1? 1. Okay. So we gotta remember we gotta add a transition from 0 to F. So we have 1 so far. Can we go around the loop on Q1? Yes, and we already saw that was 2 star. What about all the ways I can go from Q1 now to QF? It's still empty, right? Empty string. So, in fact, now we have the regex, 1, 2 star, because it's exactly the same as the other one we did. And since we handled both transitions, now I can erase the rest of it, these unneeded transitions. So I'm going to nominate a state to rip out. I'm going to rip out QS. Can I rip that out? No, why not? It's the start state. So, okay, so I clearly got that wrong. Nominate for me another state to rip out. Q0, perfectly good. So Q0. Oh, another thing. This entire process, did we have to use some intuition as to like how we made the transitions, or was it a mechanical process? It was a mechanical process. So could a computer do this? Yeah. Cool. So we want to rip out Q0. So our little diagram again. And let's make our in Q0, out Q0 lists. So what are all the ways I can enter Q0 from somewhere else, some other state? Well, the start state is 1. Is there another one? Q2, that's another one. What are all the ways I can go to leave Q0 going somewhere else? Going to some other state. Q2 and QF. So how many transitions do we have to add now? 4. So the choice of which state to rip out may make some later steps easier. So maybe we could have made a better choice at the beginning to avoid 4 transitions. I actually don't think we can. But if we had some other NFA, it might have been an easier process. But no matter what, if we apply the process correctly, we will get the right a correct regex out of it. So let's do QS to Q2. So there's nothing on the transition yet. So I'm going to use green for this to indicate the second step. So what are all the ways from QS into Q0? Epsilon, so there I just wrote it. What are all the ways I can loop Q0? Is there a loop on Q0? Yeah, just the 0. So how do I indicate that? In a 0 star for the regex. What are all the ways I can go from Q0 to Q2? Well, we just made that transition, which is 1, 2 star. So I put that there. Okay, so we handled that one. That's good. Let's handle, let's say, QS directly to QF. So we don't have that transition yet. This diagram's looking a little messy already. So let's do it that way. All the ways in from S to 0, well, that's just empty, so I just wrote it. We figured out that the loop was 0, so we indicate that with 0 star as before. All the ways now from Q0 to QF, which is 1, 2 star. Just follow the transitions, or what's labeled on the transitions. Okay, 2 down, how many to go? 2, good. So Q2 to Q2. Oh, what is that usually called when you go from the state to itself? A self loop. Do we have a self loop already? Oh, what do we do? I can take the Q2 self loop route, or I could take this convoluted route. How do I indicate or? Union. So it'll be 0 union stuff. In fact, I'm just going to rewrite this transition below to make it easy. So it's 0 union something. So what are all the ways from Q2 into Q1? Well, that black transition, which says 1 on the transition. So I write 1. All the ways we can self-loop on sorry, it was Q0. That was my mistake. Q2 to Q0. Well, that transition was 1. Self-loop on Q0, we already saw that that was 0 star. All the ways from Q0 back down to Q2. 1, 2 star. Okay? Any questions so far? Cool. Not much more. Q2 to QF. Oh, we already have a transition there, but it says epsilon on it. So that means I can ignore it, right? No, why can I not ignore it in this case? Because I'm unioning with it. If I'm concatenating with empty string, that does nothing to the string. But if I union with the empty string, are those two different things? Yeah, potentially, yeah. So try not to do any simplifications if you can, especially in the epsilon union something case. So epsilon union stuff. So let's see. It's from Q2 into Q0, because that's the state we ripped out. We already saw that that was a 1. Any self-loop on Q0, which is 0, so 0 star. And anything from Q0 now to QF, which is 1, 2 star. And in fact, now we handled all 4 transitions. So now we can actually remove all this mess. Hopefully without erasing everything. Okay, so that is our, yeah. What's that?
From the transition Q2 to QF, why don't you mean with 1 start?
Because it was 1 to get into Q0, 0 star when we looped originally at Q0, and 1, 2 star either go back down to Q2 or to QF. It was the same. Other questions? Oh, so which state should I rip out? Should I rip out QF? No. So which state should I rip out? In fact, we only have 1 here. It seems like our regexes are getting a little long, right? Right? So if I do like the star of this beast, then concatenated with 2 other regexes, that can be a long regex, right? Do you think we can do something about that? Here, probably. So here's what you're allowed to do on homework and tests. Call R1 to be that regex, call R2 to be that regex, R3 to be that regex, R4 to be that regex. And then now our picture's a lot nicer. So I'm definitely going to have a single transition if we rip Q2 out. But what will be the regex on the transition? Well, either I can take the top half, or I could take the bottom path. So how do I write that? Yeah, so what will be the final regex? R1 union R2 concatenated with R3 star, because I can take that loop as many times as I like, R4. Okay, you are completely allowed to do that if your regexes are getting a little long. And it cleans up the picture nicely. So, am I done? It seems like it, right? Is this a regex? Sure. Did I just circle a GNFA? What do we actually want out of this? We want a regex, right? So you actually need to say the regex is R1 union R2 R3 star R4. Because many students in the past have circled that and said, there's the regex. So it demonstrates a lack of knowledge of what is a GNFA and what's a regex. But if you say the regex is, or you can point to it on the transition, that's okay too. But you can't just circle the entire thing and say that is a regex because it's not actually one. Yeah.
Can you go back up?
Yeah, sure.
Thank you.
Yeah, so as I was just saying, make sure to say the regex is either point to it or actually just rewrite it. Either way is okay. But in fact, now we can convert from an NFA or a DFA to a regex. So what do we know about the languages that regexes recognize or describe? Oh yeah, they're the same as regular. How do we know that? Yeah, because we can convert back and forth between NFAs. And what do we know about NFAs? They're equivalent to DFAs. How do we know that? Because we can convert an NFA to a DFA, and every DFA is already an NFA. So in fact, we can convert back and forth between any one of those three. So from this, we can conclude that regexes describe exactly the regular languages. Nice. So the regular expression actually does carry some weight there. It actually does mean regular languages here. So what about this computational problem? So A sub rex, so instead of A sub DFA, I have A sub rex, which means, no, not M. So I have a regex, and this X string is described by R. So in fact, X is in the language of that regex. So what do we know about this problem? So someone that said it's decidable. Is it decidable? Yeah, so how do we know that? So is decidable. So how do we do it? Well, we take this R and X, then we say, well, what do we do with that regex? Well, if I turn it to a DFA, that's great. Well, do we have a procedure that converts it all the way to a DFA? No, we have a process that converts a regex to a NFA. Okay, so convert R to an NFA, let's call it N. Oh, but wait, do we have a procedure that converts an NFA to a DFA? Ah, okay. So let's convert N to a DFA, let's call it D. Now what do I do? Oh, run the decider for A sub DFA on this DFA and the string that we want to consider. Or we can just run the DFA directly. So let's run the DFA directly on X and answer what D says. The important thing here is that the first two conversion steps, or the conversion steps, don't change the language along the way. The NFA has the same language as the regex, and the DFA has the same language as the NFA. So the answer actually is the same for the regex. So in fact, it's decidable because both of these first two steps take a finite amount of time, and running a DFA on an input obviously takes finite time, as we know. So in fact, A sub rex is decidable. What about A sub NFA? Like if I have an NFA in an input, is that decidable? Yeah, so what do? Just convert it to a DFA and then run the DFA on it. Okay? Cool. Any questions about that? So let's see, how much time? So I have enough time to start the next one before we take a break. But you may be wondering, well, we talked about these decidable and recognizable things way back at the beginning, I guess not that long ago. And then we talked about LBAs, which we showed don't have the same languages as arbitrary Turing machines because we could decide A sub LBA, but we couldn't decide A sub TM. But we also noted we couldn't decide E sub LBA, the emptiness problem for LBAs. But for DFAs, we could decide both of those, A sub DFA and E sub DFA. So we can actually show, because of that, the regular languages are not the same as the languages described by LBAs, or the decidable ones. So there must be, for example, some decidable language that's not regular, right? Because if they were the same, then the computational power of DFAs would be the same as LBAs, but the emptiness problem is different for LBAs than for DFAs. So you may be wondering, okay, there exists a non-regular language that's decidable, but we haven't seen one yet. So let's think about this language. So it's the language of strings over 0, 1 star, such that you start with some number of zeros and you end with the same number of ones. So for example, the empty string's in there, 0, 1's in there, 0, 0, 1, 1's in there, and so on. Could we try to get a DFA that has this language? Well, it seems like if you have a whole bunch of zeros at the beginning, then we have to somehow remember that we have the same number of ones at the end, and we need to check that they have the same number of ones as we just saw zeros. But do DFAs remember anything? No. Well, remember in this sense means in which state it's in. Well, what we could do or try is just to say, well, if I have a whole bunch of zeros, I can do something like this, and then I can just do the same type of process with ones. And then we better not accept anything after that. Will this idea work? No, why will it not work? Right, the number of states is fixed. So if I feed an input that's one more 0 and one more 1 longer, then that string should also be in the language because that's what the language says, but this NFA now will definitely not recognize that string. And so it seems like, well, we can have an unbounded length of input to work with, but I have a fixed number of states to work with. And I can't remember anything like on a tape, for example. Could I decide that language using a Turing machine? Yeah, so what we do is just mark a 0, mark a 1, mark a 0, mark a 1, and hopefully we get the same number at the end. We've seen how to do something similar to that. So it's definitely decidable, but in fact what we'll show is that it's not regular. There's no DFA for this language. And you may think, well, this idea of remembering things seems like a sufficient explanation for why it's not regular. So that's kind of a red herring. So just because one idea doesn't work, that does not preclude any other idea from not working. So there's actually one of the problems in problem set 4 tries to address this, that if you change the alphabet and have the exact same description of the language, changing the alphabet can distinguish whether it's regular versus not regular. So that's what that question is trying to address. But there may be some other idea that some DFA could recognize this, right? So maybe some other DFA could. So I don't know what that DFA looks like because it doesn't exist. But let's suppose it did exist for now. And it must have some final states because the language is not empty. But let's suppose the DFA looks like this black box. And maybe what we can do is, notice back at this example, we built it to work with a particular type of string, and then we fed in a longer string, and then we forced this machine to not have the correct answer. Like before we fed in a string that had one more 0 and one more 1 at the end, and that this NFA should accept it, but it actually didn't accept it. So if we have a fixed DFA like this, then maybe what we want to do is we want to, suppose we accept a string, and then we force a longer string to be accepted as well. And if we guarantee something about the properties of those strings in the language, maybe we can try to approach this type of question. So the way that we'll try to address non-regular languages is to think about what types of strings are accepted by DFAs, right? So if I have a fixed DFA, what types of strings, what's the structure of the strings in the language? And so we'll talk about that after the break.